Welcome Mechanics of Materials students. In this demo problem we'll be examining normal strains given a known displacement and a known geometry. So in this problem we have a couple of bars and they're deformable. We'll assume they have a very low modulus so we can stretch them. And this plate, which I'm going to kind of outline in red here or color in red, we're told that this is rigid. So what this means is we can assume that this end plate isn't going to deform. It is a rigid body the way we viewed bodies in statics. It's not going to undergo any deformation, whereas bars A and B are. Another way of thinking about that, and this is kind of thinking ahead towards Hooke's law, elasticity, which will be our next section after strain, we can think of the rigid plate as having a very, very high modulus compared to whatever the material is in bars A and B. So when the plate moves, it will translate. In this case, it's not going to rotate because we were applying the same force to both ends, so we're not applying any moments. So the rigid plate is going to undergo translation in this direction. And that means we're going to end up stretching bar A, and eventually if we displace this rigid plate enough, we're going to end up starting to compress bar B. So we're asked, what are the strains in bars A and B if the rigid plate moves 0.0236 inches to the right? And so this is in the direction of my red arrow. Okay, so again, we're looking at normal strain. We're not shearing it. If the plate moved up, we would end up inducing a shear strain on bar A, but it's moving to the right, so it's going to stretch it, kind of an axial strain. So E normal bar A is going to be equal to, we'll call it delta L bar A divided by L0, original length of bar A. So our original length is pretty easy. We're given that as 60 inches. And it actually is easier to determine the change in length of bar A because honestly, as this rigid plate moves over into the right, that displacement of the rigid plate is actually accomplished by stretching the bar. So basically, if you think about it, you got your bar, and as you displace the plate, you're actually stretching the bar. So find a better way to draw that. Maybe intuitive here. So here's our original end position of the bar, and then the bar gets a little bit longer here. This was the original position of the plate. So it goes over, and so the bar assumes a new length. So this was the original length, and now this is our final. So the stretch in bar A is just literally equal to the translational displacement of our rigid plate. So it's 0.0236 inches. So strain is equal to the ratio of those two. So we have 0.0236 divided by 60. And we're going to express this in terms of microstrain. So what we get out of our original ratio is 3.933 times 10 to the minus 4. And of course that's a dimensionless value. Strain has no units. We're going to multiply this by 1 times 10 to the 6th. And that'll let us basically make this look a little bit easier to express. So we end up with 393. We call it microstrain. There's no units, but we are indicating that this has been multiplied by 10 to the 6th to get this number. Okay. So that's strain A. in the normal direction. Now B is a little bit different only because we have, we'll change colors here. We'll go green for B. Because we have this 0.02 inch gap between the leading edge of this rigid plate and where we begin to contact bar B. So the plate's going to have to move 0.2 inches of its total 0.236 inches of rightward displacement before it even starts to compress bar B. So the total travel distance of the rigid plate, which is going to contribute to any kind of strain of bar B, is just 0.0036 inches. So basically the plate's going to travel 0.02 of its 0.0236, and then it's going to travel another 0.0036, and that will end up being the total compression of bar B. So that's the only real trick to it. So if we look at the normal strain of B, we can say the final length of B minus the original length of B divided by our original length of B. The final length is going to be shorter than the original length, and it's going to be shorter by 0.0036 inches. So the distance of travel of the rigid plate minus the gap that it had to travel to begin to impinge on bar B is actually the compression, or the negative stretch, we'll call it. So the numerator of our strain expression is simply 0.0036 inches, and our denominator is the original length of 24 inches. And when we run that ratio, we end up with, again, in the hundreds of microstrain. We'll just multiply it out to make sure. So we have 0.0036, enter, 24 divide, 1 times 10 to the 6 times. Yep, confirmed, 150 microstrain. And that needs to have a negative number because this is actually, the final length is less. Just remind ourselves, length final of B is less than length original of B. Therefore, EB is less than 0. It's a negative number. So we have positive microstrain on A, or tensile strain, and we have compression negative normal strain on B. So that is it for this example, and just a review of normal strains based on displacement of one portion of, in this case, two bodies.